And what is what is the Jacobson radical? Or we may Can you see at least at least some evident ideals there in this triangular ring? Maybe even two-sided ideals. So put here 0, yeah?
No, put 0 on to both.
Here and here. Well, I don't think, but well, let's try. Let's try, but like this, yeah? You see, when you take here AM, yeah, so you multiply by elements, you multiply this line, yeah, so it's not an ideal.
It's a left ideal.
It is, yes, probably, yes, it is, yes, if you multiply, yeah, because you multiply this column, yeah, it is a left ideal, yeah, but it's not a two-sided ideal. So strictly upper triangle, yeah? Линия? Какой? М и Б. Okay. Okay. Well, I don't think so, but well, let's try. You see, when you multiply by yeah, maybe you're right. Maybe you're right. Just a second. If you or maybe yes, maybe you're right. So when you let's see. So when you multiply this column, you always get zeros, yeah. So it's okay. So it is a left ideal, and when you multiply this row by this column, you get 0 because 0 is here, and when you multiply this, wait, when you multiply, but anyway, it's upper triangular, so we don't care about this, yeah, so it's okay. Yeah, you're right, so it's an ideal. It's a two-sided ideal, yeah, okay. But we want, yes, but as Sasha told us, there is, wait, we are looking for maximal ideals, yeah, so it's, yeah, so we can put here, but two-sided ideal, yeah? Any two-sided ideal, yeah? So I is a two-sided ideal, Okay. So actually, if we want all right, but then we want this to be yeah. So if we want, so it will be maximal. So it is maximal. Well, as a left ideal, yeah. For instance, as a left ideal, if I is maximal, yeah. Yeah, that's correct. But then, okay. But then we also want to produce more maximal left ideals. Can you see more? На B. Okay. So we take A, M, I. So here I is a maximal left ideal, yeah. So is that a left ideal? Yeah. Oh, why not? Okay. All right. So what is the conclusion? What is the intersection of all these ideals? Maybe I should erase this, yeah, just in this form, yeah. So what is the?
So A and B not simple.
Yeah, because we I think that's enough to conclude to find the Jacobson radical. Because we have already a supply of maximal ideals, yeah, here. So we just want to find the intersection. So, and what would be the intersection?
Jacobson radicals on the diagonal.
That's right. Yeah, then we will have to check that. Yeah, so M Jacobson of B. Yeah, so and in the case of semi-simple, we just have zeros on the diagonal. Yeah. All right. So in particular, if so, we want to see some examples when we want to know whether something is Noetherian or Artinian and so on. Yeah. So let's look at some examples. So essentially, for instance, if A and B are semi-simple, maybe or maybe even fields, yeah. Yeah, so that there will be no ideals. But so A. So what can we say about? Well, I think it's enough to conclude what can I say about Artinian or Noetherian properties of this ring. So how could you describe them? So we may assume that that we know whether A and B are Artinian or Noetherian on the right or on the left. So can you maybe well, to be more concrete, let's assume that that what? So that B is a field. B is a field. A just a subfield. M is B. And what else? Then we we may say what kind of field extension is this A and B. Yeah. So, and suppose that this degree of this extension is infinite. Yeah. So what can you say about this ring? Is it left, right, Artinian or Noetherian? So you see that maybe let us make some very general remark or maybe a lemma. So for any, so if we take a rather arbitrary abelian category, and consider just a short exact sequence. So 1, 2, 3. Then M2 is Artinian or Noetherian. If and only if both M1 and M3 are Artinian or Noetherian. 1, 3. Okay. Well, I mean it's rather trivial remark, yeah. So in our case, we have our module R, yeah. So it is a module over itself, yeah, and it has the semi-simple quotient. It's semi-simple. What is its semi-simple quotient? Well, not semi-simple, but the quotient by the Jacobson radical. Yeah, so we can write here Jacobson radical. And what is the quotient? So we just erase m, yeah? We erase m, so what is left is a plus b, yeah? So just a plus b. Что там? Yeah, that's right. Yeah, you're right. Sorry. Yes, you're right. Yeah, that's right. Yeah, so and you see that to see whether this ring is Noetherian or Artinian, we just have to look at these two rings, yeah, and to the Jacobson radical, yeah. So when our A and B are semi-simple, yeah, like fields, then there is no problem. They are, of course, yes, they are.
So how do we define Artinian and Noetherian objects in abstract theory?
In an abelian category, well, you just have a sequence of monomorphisms, and you may ask whether so you have an object here. So for instance, if we are looking for a definition of Artinian objects. Yeah, so we can consider sequences of or maybe collections of monomorphisms m alpha, m beta. Yeah. And we say that this sequence or this collection, this chain of, so we can define chains of monomorphisms, and we say that chain stabilizes if at certain point monomorphisms become isomorphisms. Yeah. So these are monomorphisms, but if Artinian means that they become isomorphisms. And similarly for Noetherian objects. Yeah. So the conclusion is that so there is no problem with this. Yeah. So if we assume that they are fields. Yeah. So it's or just any semi-simple rings. Yeah. So they are, of course, Artinian and Noetherian. Yeah. So they are finite length. Moreover. Yeah. They are finite length. So the only question is what is about Jacobson radical. So what can you say about Jacobson radical in this case? So what does it mean that we consider this ring as a left module over itself? So actually we deal with the module M, yeah, in this case. So what does it mean that we consider M as a left module over R? So I remind you that M so it is a left A module and a right B module. Yeah.
Just left A module.
Yes, that's right. So if we consider M as if we consider this as a left module, then this is just an A module, yeah, a left A module. Yeah? And if we consider it as a right module, then it is a right B module. Yeah. So the question is whether M, in our case, this B is Noetherian or Artinian as a module of itself, a field. Yeah. A field as a module of itself. Yeah? So it is, of course, yeah. It is. But if we consider it as a module over a subfield like this, yeah, if we consider it as a module over the subfield A, is it Artinian or Noetherian? No, it is infinite. It is an infinite dimensional vector space. Yeah, so it is neither Artinian nor Noetherian. But actually, you see that in this case, this module is simultaneously either Noetherian and Artinian or non-Artinian and non-Noetherian. Yeah, and there is a reason for that. Yeah, so that actually these two properties are related under certain assumptions. We will see this hopefully soon. But just a second here. How good. It's here. I think it's here. Yeah. It's here, here, here. All right. Yeah. So let us. Let me recall you what we did last time. Last time we have checked certain characterization of the Jacobson idea, Jacobson radical. This is a reminder. Characterization. This is characterization. Characterization of Jacobson ideal. So we assume that A is left Artinian. And then Jacobson radical is the same, has the following. So, well, we have defined it as intersection of all maximal left ideals, but it turned out that it is the intersection of all maximal right ideals. Yes, and this two-sided. It is the smallest ideal such that the quotient is semi-simple. Semi-simple. And another characterization is that it is an nilpotent ideal containing all other nilpotent ideals. Nilpotent ideal, two-sided, of course, two-sided, containing all nilpotent ideals. Yeah. So, and what can we do with that? We can deduce the following consequence. Namely, under the same assumptions, so we assume that it is again left Artinian. Next, M is a left A module. And then, so this is a criterion of the semi-simplicity, yes? So then M is semi-simple if and only if it is annihilated by the Jacobson radical of A. So the proof is quite evident, namely if M is semi-simple, then it is a direct sum. So if M is semi-simple, then it is a direct sum of certain simple modules. Yeah. Then you know that the Jacobson radical is just the common annihilator of all simple modules, yeah, and therefore it annihilates the direct sum. So we know that mi are simple, and therefore each summand is annihilated by the Jacobson radical, yeah, and therefore it is this Jacobson radical annihilates the whole direct sum. And conversely, if this module is annihilated by the Jacobson radical, then we can consider this M as a module over the quotient. Yeah, so it can be considered that as a module of over the quotient of this ring by its Jacobson radical. Yeah. Там холодно. But you see, this. So we use this first characterization of the Jacobson radical. Yeah. So we know that this is a semi-simple ring. Yeah, and what does it mean that this is semi-simple? It is, as a module over itself, it's a direct sum of simple modules. Yeah. So it is, and therefore, so we can write so that this is isomorphic to direct sum of simple modules. And therefore, any module over this ring is isomorphic to direct sum of certain copies of these modules, yeah, and therefore they are direct sums of simple modules, and therefore it is any module is semi-simple. So any module is semi-simple. Okay. Yeah, maybe one more consequence of this characterization, that any, well, again, rather trivial, but just to get some familiarity with this stuff. So we assume that A is left Artinian, and then the claim is that any A, no, say left, yeah, any left A module is semi-simple, if and only if it has no nilpotent, if it has no non-zero nilpotent ideals. Yeah, so this is just the second characterization. But maybe one more remark. So far we did not. Let me give one more definition, namely. So definition. Well, again, an associative, as usual, associative ring is simple. You see that we have similar terms like simple, semi-simple, and they mean slightly different things. Yeah, for instance, there is no evident relation between simple, semi-simple, and we have the notion of simple module and a simple ring. They are not. They are rather different. Yeah. So an associative frequency symbol, if it has no, if the only let's call it A, the only two-sided ideal, two-sided ideals in A are itself and 0. So, and then just as a continuation of this simple corollary, that in particular any simple, so I just said that there is no relation, yeah, so but there is no relation, but there are some exceptions. So if we assume that that A is Artinian, then that in particular S left Artinian simple ring is semi-simple. Let's see. Ring is semi-simple. Okay. So you see, for instance, a simple ring need not to be simple as a modulo of itself, left or right, yeah? So let me give you some examples. Or maybe you know, do you know some examples of simple rings? Do you? You definitely know. Maybe you don't know that they are simple, but can you imagine an example? Кто? Polya. Yeah, that's right. Some NSQ field examples. Examples of simple rings. Yeah, simple rings. So yeah, so we assume that D is a division algebra, division ring. Yeah, SQ field. Yeah, because there are not that many ideals. Yeah, just left or right. Yeah, but can you generalize this? Well, just consider matrices. Yeah. Matrices. Then matrices n times n matrices is simple. Yeah? Have you done this exercise to show that so the matrix ring is simple, yeah? So there are no two-sided ideals there. Well, if we have never done this, then this is an exercise. Yeah, you have to do this at least once in your life. Yeah? So it's not difficult, of course. Yeah, maybe there are more examples. For instance, you see that in a sense these finite dimensional. Yes, of course, this is a finite dimensional as a vector space over this skew field, as a left or right, whatever you want. But there are more examples, like, for instance, you see that, of course, this is Artinian, yeah, because it is finite dimensional over skew field as a left or right, whatever module. Yeah, but let's consider. The following, I forgot how it's called, some kind of polynomial rings. So so this is example number 1, and another example is the following. So we take a field, we take some letter, some variable x, and we take an endomorphism of so a field endomorphism, and consider the following. I don't remember how it's normally denoted. Let's call this something like this. Yeah. So as a left vector space, this is just so this as a left K vector space. This is just the ring of polynomials. But so what do we want? We want to define the multiplication. Yeah. So of course you know how to add to polynomial. Yeah. So the addition of polynomials is defined. By the way, what is a polynomial? Yeah. The polynomial is the following thing. It's a0, a1x, and so on, plus an to the big X. Yeah. Big X. Big X to the n, yeah, where all these AIs are in the field K. Yeah, the only question is how do we multiply them? Yeah, so we have to know how to multiply. Well, we know how to multiply x by a on the left. Yeah, just take like this. We have to know what is this. And this we define, and just we have this sigma, so we act of this, we apply sigma to the A and put it on the left. Yeah, so this is, so we do this like this. Oh, I'm sorry, it's not simple. It's not simple. It is. Yeah. So the question whether. So what can I say about this ring? So actually, what kind of questions can we ask? First of all, can we say that it is Noetherian? Well, of course it's not Artinian, yeah, because well, you can imagine some yeah. So for instance, if we look at left ideals, yeah, we can, of course, we can well, let's call this R or A, yeah. So we have so A is strictly contains AX, yeah, strictly contains AX square, and so on, yeah. So it is not left Artinian. And maybe you can imagine that it is not right Artinian, yeah, because why? Because well, of course you can do the same thing. So you can put x on the right, yeah. So on the left, sorry. So and this will also be. So when you, of course, this is a strictly descending sequence, yeah, because when you move x to the right, you get. So actually, you can see that this is a subset. Is that correct? This is a subset here, yeah. Is that correct? Because you just move x. Or powers of x move to the right using this rule, yeah? And that's how you get this inclusion. Well, you might ask whether these yes, you might ask whether this is inequality, yeah? Can it happen to be inequality? Yeah, that's right. Yeah. So if sigma is bijective, then these ideals are two-sided. Yeah. So the interesting case is if it is not, yeah, because so it is, yeah, it is. You might ask about. By the way, is it yeah. So. Yeah, so actually you might ask whether it is Noetherian, yeah? Say left Noetherian or right Noetherian. So, what do you know about usual polynomials? So suppose that sigma is the identity. So what can you say? Is it? What can you say about this ring? Yeah, that's right. It is a principal ideal domain. Yeah. So you might ask, is this a principal ideal domain in some sense? For instance, is it true that any left ideal, any left or right ideal is principal? So do we have any kind of Euclid algorithm? So what do we want? We have two polynomials, P and Q. So here we can also define its degree, yeah? So suppose that we have P and Q, and degree of P is at least the degree of Q, degree of Q, and then well, maybe, yeah. So can we write P as a product of well, either this way or this way, where degree of R is strictly smaller than degree of Q. So what is P? P is a n x to the n. So this is n, this is m, and this is P. And Q is bm x to the m plus something. Yeah. So the question is, can we multiply Q by something? Can we multiply this term by something to get this term? Can we? Wait, we have two options. Either we consider left ideals or consider right ideals. Yeah, so when you say that it depends on sigma, then what do you mean? In which case? What? Is there any case that does not depend on sigma? Can you just repeat the question. Can you multiply Q by something, either on the right or on the left?
Слева не зависит, справа зависит.
Okay, so what is this? What should be a multiple of Q on the left or on the right?
Обратно к сигма bm.
Wait, никакого сигма.
Мы хотим слева домножить.
Слева, так, на что?
Ну вот, старший член будет в степени n-7. И мы должны домножить, у нас bm принесется и вынесется сигма от bm.
Wait, we have to get rid of this bm.
Да.
We have to multiply by its inverse.
Но у нас bm принесется под действием сигма.
Yeah, but it's not a problem. We know how to x. We know the rule, but we don't need to write this multiple in the standard form. We can write it anyhow. Yeah. Just write it somehow, and then we can use this rule. Yeah. Слева. This is on the left, yeah. So we multiply on the left. So we get rid of this bm. So we write that it's q multiplied by inverse multiplied by the difference in powers of x and multiplied by an. Yeah, and this way we get rid of this maximal power and continue this way. Yeah, so it's so the conclusion it's this is so this works. This works, but and the conclusion is that any left ideal, yeah, any left ideal is principal. Left ideal is principal, and therefore the ring is left Noetherian, yeah. So what about right Artinian? Is it is it right Artinian? Well, maybe also leave it as an exercise, yeah. Well, of course, you know the case when it is an automorphism, then probably there is no much difference, yeah, between left and right. But if it is not, then this is unlikely, yeah, because all right, okay, but let's ask another question about the same. You see, we started with examples of simple rings, so the question is whether this is simple. Of course not, yeah, because for instance, if sigma is if sigma is bijective, then we already have a supply of non-trivial two-sided ideals, yeah. So we assume that sigma is not bijective. So sigma of k is not k, yeah. So and the question is, maybe I should not, yeah. Wait. Is that correct? By the way, is that correct? I'm sorry. I'm sorry. I wanted. I wanted slightly more general thing, namely, yeah. Yeah, actually, maybe we should generalize this slightly. Excuse me. So actually, there will be not one endomorphism, but some pair actually. So let's start with the same picture. So this part of the picture. So we consider certain left k-vector space as usual, the polynomials, yeah, as usual. But we want. So you see, we have the notion of degree, and we want to define the certain multiplication such that degree of the product does not exceed, roughly is equal to degrees to the sum of degrees of the multiples, or is not at least is not bigger, yeah. And so the only problem is here. How can we define xa? And to define it, we using this condition, we actually have to define it somehow with it's a certain multiple of x plus a certain constant. Let's call it psi a. Yeah. And then the question is, what are the conditions? So so far, you see that here we assume that it is a field endomorphism. Well, let's erase this condition, yeah, and just look at this condition. And what do we want? We want associativity, yeah. So we want that x a times b is the same as x times ab. Yeah. So what's written here? Here it's written ab sigma x plus xi of AB. And what is written here? It is a sigma of times xb plus xi a times b. So we continue this line. So it is a sigma b sigma x plus a sigma xi b plus xi a times b. So you see that, and this is the same, yeah? So the conclusion is that sigma should be multiplicative, and of course, yeah, and of course this is for associativity, and also we want to have distributivity. So xn of a plus b is, of course, we want this to be xa plus xb, and therefore both these and this should be additive, yeah? So so these conditions actually imply that sigma is a field endomorphism. And xi, you see that that xi is a sigma derivation, and xi is a sigma derivation. So, for instance, if sigma is the identity, and then you get precisely the Leibniz rule, yeah. So this one. So you see. Что?
Если мы хотим, чтобы это было сигма.
Yeah, if sigma is the identity.
Да.
And this is, so here, so in general I write here sigma derivation.
Если мы так пишем, мы хотим, чтобы b тоже было под действием сигма.
Ну, значит, не хотим. Ну, well, let's put here. Yeah. Okay. Yeah. So. Yeah. So, for instance, yeah. So, and what will be the difference here? Actually, there will be no difference. Yeah, because the same argument. We multiply. So we also have this Euclid algorithm. Yeah, just again multiply on the left by the inverse of Bm. Yeah, and then so there is no problem here at all. So it is of course left Artinian. All right. So, yeah. Now let's try to see whether it can be simple, or what kind of. So you see that is yeah, maybe we should put here xi as well. So it is, yeah. So, for instance, we start with we have some polynomial like this, yeah. Yeah, well, Okay, yeah, of course, maybe it's, you see that it's not simple, but maybe we can modify this. Maybe not this, but rather previous example. So you see that, yeah, maybe coming back to previous, namely to matrices. If you remember, matrices over a field. If you remember, when we discussed Galois theory, then we started with a field. So it's well, again, it's a reminder. And G was a finite group, finite field automorphism group of K. Okay, and then we considered a certain skew group ring, and it turned out that this is the same as matrices of the size equal to the order of this group with entries in the fixed field. Yeah, so this is this was this ring was actually a matrix ring over a certain field, over the fixed field. Yeah, and we know, or hopefully, well, I hope you will do this exercise to show that this is a simple group. But let us look instead of matrices, let's look at this ring, but maybe in a slightly different setting, namely we will not assume that G is finite. Yeah. So let's look at. So let's say I be an ideal K of G. Well, maybe non-zero. Non-zero ideal. And a I G I will be an element there 1 to n, and we assume that first of all that is of course non-zero, and n is minimal. Well, you can say that n is n is at most at least 1, yeah, because otherwise nothing to sum up. But if n, so the idea is that if n is 1, then actually this element generates the whole ring. Yeah. So you can think of minimal as at least 2. Yeah. But can you show that actually n is equal, indeed is equal to 1? Maybe let me state so now Well, you see, you have an element, yeah. So it is n is minimal. This means that all these AIs are non-zero, yeah. And you may assume that a n is 1, yeah. Okay. And then you may, or maybe A1 if you wish, A1. You may, next you may multiply, so you may multiply by G1 on the right, on the left, whatever you want. Yeah. So you may assume that G1 is 1. Yeah. Let's call it alpha. What else? Then you may multiply by elements of k. So what will be the difference? So so A alpha, what is A alpha minus alpha A? So A is an element of K. Oh, maybe it's not even important here. Maybe it's we don't need this one. Yeah, just G1. I assume that G1 is 1. Yeah. Or not? Yeah. Just multiply it. So we multiply this on the. So may assume. So just multiply alpha by G1 inverse, yeah. Что все? Yeah.
And we have something that happens smaller than
Yeah, but we have to make sure that it's not 0. Yeah. Yeah. So yes, you're right that this is the sum from 2 to n. This will be AI minus maybe let me write this way. So it will be AI A minus A GI GI. Yeah. So but yeah, of course we assume, yeah, so is minimal. So first of all, we of course we assume that they are all these coefficients are non-zero, but also we assume that they are pairwise distinct. Yeah, so Ji is not Jj for all distinct indices. Yeah. So in particular here, we assume that Gi is not identity for all indices starting from 2. Yeah, and this means that there exists A such that it's not fixed by J2. So J2 is not A. Yeah, and therefore this is not 0. Yeah. So this is an example. You see that this is an so far we we had only this type of simple rings, but they are all finite dimensional in a sense. But also there are infinite dimensional like this. If we take some infinite automorphism group, then of course we get an infinite dimensional simple rings. But we will see that actually all finite dimensional or Artinian examples are of this type. Yeah, so that's the point. So that actually there are not that many simple rings. So they are all more or less related to skew fields and matrices over them. Okay, so yeah, so this is, yeah, so the conclusion was, I have already raised it. Okay. Well, maybe maybe yeah, that's it. Now let us call one more definition. One more definition, or maybe maybe yeah. So again, we start with an associative ring A. Well, we have so far we have a notion of a simple ring, but also we need some kind of general, well, you see that in Artinian case we have a characterization of Jacobson radical saying that it is a maximal nilpotent ideal such that it contains all other nilpotent ideals, and the quotient by this ideal is semi-simple. Yeah, so we can extend a class of Artinian rings in the following way. We say that this ring is semi-primary. Semi-primary. If Jacobson radical is nilpotent, and the quotient is by this radical is semi-simple. So A is semi-simple. Yeah. So the example of a semi-primary ring is left Artinian rings, yeah, because of this characterization of Jacobson radical, yeah. So this is example. Example, any left Artinian ring is semi-primary. Semi-primary. Okay. Okay. Yeah, so now the claim is that what is good about semi-primary rings is that for them the property to be Artinian and Noetherian are related. They are more or less equivalent. So it is Akizuki, Hopkins, Levitsky, Akizuki, Hopkins, Levitsky. So we assume that A is a semi-primary. And we consider a left A module M, and for a left A module M, the following properties are equivalent. So the first condition is that M is Artinian. Next, it is Noetherian. Next, it is of finite length. And finally, that it is finitely generated. Okay. All right. So actually, you see that we have skipped one quite evident but important thing, namely Jordan-Hilder theorem. So you see that in principle it is it would be natural to remark that 3 implies immediately both 1 and 2. Yeah. So if but the only subtlety here is that what does it mean for finite length? So we have to know that this is well defined. Yeah. So it's what does it mean that something is? What is the length?
Length of model.
Yeah.
By definition, it's length of maximal length of ascending.
Yeah. So length. So you there is notion of composition factor, composition series. Yeah. So it's if we have an object M and how do we proceed? Yeah, so we say that it is of length m if it is inequality. So definition would be of composition series. Yeah. So composition series of m is a sequence m naught starting from well, of course, you may ask where do we live. Yeah, so we may live in certain category of well. Here we deal exclusively with certain abelian categories, so, but in principle, composition series are also well defined for groups or X group and so on. Yeah, so we start with a zero object, which is then we say that it is embedded in M1 and so on, Mn, which is M, and it is a composition series if the consequent quotients are simple. And this n, yeah, and then the claim. So it's Jordan Holder that n is independent of a composition series. Is independent of you may remember that at the very beginning we have proved this Jordan-Holder theorem, at least for groups. But of course you can prove it in more for abelian categories. There is a version which does not really assume that length is finite. There are some versions, but anyway, we claim that we assume that this length is finite. So n is, so Jordan-Holder says that n is independent of a composition series. And therefore we can define length definition. So the length of m is this n. Yeah, so this number of elements in this composition series. Okay. Yeah. So and therefore, of course, 3 implies 1 and 2. Yeah. Next. Yeah, and of course, if m is Noetherian, this means that m is finitely generated. Yeah. This is trivial. Yeah, because okay. So now let's prove that 1 implies 3 and 2. So this is evident. So this is evident. So this is Jordan-Holder. This is Jordan-Holder, and this is evident. Yeah. So and 2 implies 2 implies 3 as well. Yeah. So that finiteness of the length implied both by Artinian property and the Noetherian property. So let's denote for brevity the Jacobson radical by J. Then consider descending sequence. So jm, j square m, and so on. In principle, this inclusion are not strict. M, and so on. Okay. Yeah, so you see that our, by definition, our Jacobson radical is nilpotent. Yeah, this means that for certain n, this is 0. Right? And these are, of course, these are left. So these are left. Left submodules. Okay. Yeah, and so we want, you see that we want to check that this m is of finite length. So, well, it's sufficient to show that these consequent quotients are of finite length. So we let's denote them by fi will be the quotient of jim modulo ji plus 1 m. Okay. But then of course fi is annihilated by the Jacobson radical, yeah, because just multiply we get 0. All right, but we know that so what does this mean that that it is annihilated by the Jacobson radical? This means that it is semi-simple. Okay. All right, and that's it. Yeah. So now you see that if it is semi-simple and Artinian or Noetherian, then it is of finite length. So if m is Artinian, n or Noetherian of finite length. Okay, so so yes, this shows that either of these properties imply that it is of finite length. Yeah, so we have checked that 1, 2, and 3 are the same. Next, we have to deduce deduce this one of these properties from 4. Yeah, so this is let's prove that 4 implies the Artinian properties. Artinian property. Yeah. So what do we know? Yeah, we know that. You see, to check that it is M is Artinian, it's sufficient to show that each of these it suffices that Fi are Artinian. Okay, but for yeah, so it's yeah, so well, sorry, sorry. Wait. Excuse me. We don't need Fi because it's easier. It's easier. Namely, yes. Yeah. So M is finitely generated. M is finitely generated. This implies that any yeah, so it is. It means that it is a quotient. So M is a quotient of finite direct sum. By something. And that's it. And that's it because wait, so it is finitely generated. Yeah, so we want, you see that, so yeah, so essentially what we want to show is that из 4 следует 2.
Из дня 2 следует 4. Просто у нас есть какая-то возрастающая бесконечная.
Возрастающая, бесконечная, да, но там, да, но как бы тут должна быть какая-то неутровость. Сейчас. Должна быть неутровость где-то здесь. То есть, вот смотрите. Вот. Yeah, you see that the point is that so we actually what we need is that M. You see, essentially, we can take as M, we can take A itself, yeah? Because A satisfies number 4, yeah? And it is equivalent, because if we know that A is Artinian, then any quotient of finite direct sum of copies of A will be Artinian as well. Yeah. So the only thing we have to check is that A is Artinian as a left module of itself. Yeah. Is that correct? Now, what do we know? We know that the quotient by the Jacobson radical is semi-simple. And semi-simple means that it is of finite length, yeah, or as a modulo of itself. Yeah, so it's okay. So the problem is in the Jacobson radical. So is y is so yeah, it is. Because here I have an opposite. Well, let us skip maybe. Anyway, we'll have to make a break. Yeah. So, yeah. Maybe we'll have a short break. Yeah. For how long? 10 minutes. Okay. Then I will try to correct this. Mm-hmm. Да, то, что у меня написано какой-то бред, в смысле, что там наоборот написано, что из Артина, что понятно, что если мы предполагаем Артинность, то, конечно, какая-то ерунда, в общем. Не знаю, что-то я тут написал. Артиновость m в случае А. Сейчас я... Ладно, давайте так, 10 минут перерыв, и тогда... Theorem, and M is of finite length. And these three conditions indeed equivalent, and of course, so they are equivalent. But all of them, of course, imply that M is finitely generated. But of course, the last condition does not imply the previous ones, because this precisely means that A is Artinian, but we don't want to assume that A is Artinian. Yeah? It's more general. The statement is more general. Yeah, that because we only assume that it is semi-primary. So Artinian property is just an example of. Okay. Now, yes. So this is. Yeah. So, no, and of course, the most important particular case is when M is the module is the ring itself. Consider the module itself. Okay. Yeah, and so corollary. So. Yeah, so corollary that so if we assume that no, it's again it's a particular case because Artinian implies Artinian property of the ring itself implies that it is semi-primary. Yeah, so if A is left Artinian, then left O, right? Right. Of course, there is no difference. Then A is left Noetherian. Then A is left. Well, actually, to pass from left to the right, you just can pass to the opposite ring. So it's left Noetherian. Artinian. Of course, at least some of you know this property for commutative rings, yeah, and here it's also true. Next, one more corollary, namely, you can ask what is the relation between left and right Artinian property. Yeah? So the claim is that if A is left Artinian, and we can formulate this as certain equivalence between two conditions. So then A is right Artinian, if and only if it is left Noetherian. If A is left Noetherian. Okay. Yeah, because and also you may ask about examples. Yeah, so you see that we well, of course, by definition, semi-primary is semi-primary rings are more general than just left Artinian, but or Noetherian. Yeah, so. But we may ask whether there are interesting examples of this. Well, actually, we have already seen this example today, namely, so example of what? Of semi-primary, which is neither Artinian nor nor Noetherian rings. Сейчас, значит, вы абсолютно правы. Да, yes, Саша, прав. Corrects me here. It should be right. Yes, right, because right Artinian. We want right Artinian, which is equivalent to right Noetherian. Yeah. Yes. So once again, left Artinian means semi-primary, and semi-primary means that well. So here, of course, is yes, it's a module. Yeah. So yes. So this means that this implies that A is semi-primary, and for a semi-primary, right Artinian is equivalent to right Noetherian. Yeah, that's right. Yeah, so what is the example? So, well, we have already seen this. It's just, I just repeat what was written before. It was maybe with slightly different letters. So, K, L over K is an infinite field extension. Infinite field extension. Okay, so first of all, of course it is semi-primary, yeah, because we know that its Jacobson radical is simply these strictly upper triangular matrices, yeah. its square is 0, and modulo Jacobson radical, this is just sum of two fields, yeah, so A modulo J is K plus L. So it's of course it's semi-primary, but as we discussed before, it is not left Artinian or Noetherian, but it is well, we know that it is right Artinian, yeah, because it's even a finite length, yeah. But we know it's no wonder that it is a finite length, because all these properties are equivalent. All right. Yeah, maybe I would like to make one more remark on something which we already discussed, namely just before we forget this, but anyway we will come back to this later, but maybe coming back to this yeah. Oh, maybe later, yeah, maybe later, but just a second. Yeah, it's here. Yeah, so yeah, so yeah, so what the next topic, yeah, but maybe before passing to the next topic, so essentially what we're going to do is so what we're going to do, we're going to study some kind of no, essentially Artinian algebras, even finite dimensional over a field. We're going to study their structure. So of course, as they are finite dimensional over a field, they are Artinian. So the quotient by the Jacobson radical is semi-simple, and so it will be modulo Jacobson radical. This will be just sum of matrix algebras over certain division algebras, division rings or division algebras over that field. But of course, and there will be this Jacobson radical, which is some kind of module over something. But the question will be whether we can split, yeah. So whether we can really think of this as some kind of sum or whatever. Yeah, but for that, I think it's convenient to discuss certain general homological algebra. Yeah, so so maybe just several couple of words about or maybe you're all rather acquainted with this stuff. No, not really. Not really. Okay. So we so what do we want? So we place ourselves to certain abelian category. So this is an abelian category. And then we will deal with certain functors from this category to some other abelian category, for instance, abelian groups or vector spaces B. So another abelian category, but in principle you can think of rather, so this will be a category of modules essentially, and this also will be category of modules. So category of modules over certain, maybe some module over of some maybe modules. These functors will be of the following type. They will be, so we have a notion of exact sequence, M1, M2, M3. And suppose that this functor is left exact. So if f is, so this is the definition if you have never seen this. F is left exact. If this sequence becomes it is a functor, so transforms this exact sequence to some other sequence, and we say that it is left exact if this sequence without 0 on the right is exact. Okay, and the question is, so what do we want? We want to construct certain functors. Derived. So we want to construct certain functors which are called derived functors. So these are also functors from A to B, such that there is a natural sequence continuing this exact sequence, namely this goes to R1 f of M1 and then R1 f M2 and so on. So then, so you may think of f itself as R naught of f. Yeah. So yeah, and of course there are. This is not the definition actually, yeah. So because there are many options in constructing these functors, but well, for instance, you can add something, some extra summons or whatever, some constant, yeah, for instance, summons, and this will doesn't, well, not really, but sometimes. Well, no, you can proceed as I said, but in principle it's not. But the point is that sometimes there is depending on the category. If category good enough, then there is some class of. If there is certain class of objects which is suitable for this functor f, then we can define these functors in the following way. So if say if there are enough objects suitable for this, well, for this functor, then this functor defines as follows. So so by the way, we will see what does it mean enough. Enough means that enough means that any object, there is enough objects suitable. Yeah. So this, let's call this this class. So this is the class of suitable class of suitables. Yeah, so enough means that any object can be embedded into an object in this class. So any m embeds into m, which is well, say I which is an object here. Yeah. And there is one case. So so there is one class of object which is suitable for all left exact functors. Well, there is, well, you can define it, but it's not true that there are enough objects in this class. So let's call them injectives. So an object is injective. An object I, yeah, is injective if the functor of morphisms to it is exact. Yeah, so strictly speaking, it's a functor from the opposite. Yeah, so it's a contravariant. So it's a functor from the opposite category to, well, abelian groups. Abelian groups. Yeah. So this such functor exact means that it is. You can see that it is always left exact, but it's not always right exact. So essentially, that means that any morphism. So if you have an inclusion, some monomorphism from n to m, and you have a morphism to I, then there exists an extension of this morphism. There exists an extension of this morphism to m, to the whole m. Yeah? So that's injectives. Maybe I'll post some problem list on injectives, but maybe just discuss a little bit what is it. Or maybe you know all this, you know, yeah. So not. Oh, не знаете. Ну хорошо, давайте я тогда say a couple of words and then we'll pass. So, for instance, the most important case is the case of abelian groups. So, so this is an exercise to show that an abelian group is injective. So, an abelian group is injective. If and only if it is divisible. Is divisible. Divisible means that well, group. If you multiply by anything but 0, so n is an integer. Well, an integer. Then this is surjective. Yeah. So this is, and then using this, so for instance, what can you say about? Yeah, so maybe maybe one more exercise that do you know what is a generator, cogenerator, yeah? Знаете, что такое кообразующий, нет? Yeah, so generate, so any a system of well, a collection of so x alpha are co-generating. Well, co-generating if well, if you assume that there are products, and then this means that any object embeds into the product of this of copies of these objects. So alpha that say some runs over a certain set. Then if any this is in the case when you have if any m embeds into the product of y beta, where y beta are well the isomorphism classes of I beta are in this set. Yeah, but well, you can actually you don't need to have these products. You can formulate this without products, but just this is maybe again maybe I'll do this in the problem list. Okay, so yeah, so an example for abelian group. So exercise. So show that that Q mod Z is a cogenerator of category of abelian groups. Is a cogenerator of abelian groups. Yep. And then what? Yeah. So. What else? Using this this category of abelian groups, one can show that actually there are enough injectives in category of any in the category of A model for arbitrary ring A. Yeah. So it has enough injectives. Well, actually, this is a general fact for yeah. So actually, I'm not. Maybe I should not any Grothendieck category. Grothendieck category. And the category of A models is just an example of. But anyways, we're not going to deal with the Grothendieck's general Grothendieck category right now. So you can think of A models, and in a sense, it is good. It is not just a good example, but in a sense, many things are reduced to the category of A models. Okay. So yeah, now we can define. Derived functors. Well, we assume that we have enough objects in a suitable for this functor class, and the claim is that the class of injectives is suitable for all left exact functors. So if we do have enough injectives, then it's okay. So then these derived functors are defined as follows. These are just ith derived functor of f is well, it is a functor of some m. It is defined as ith cohomology of the following complex. You take an injective resolution, so I0, I1, and so on, be in a suitable, a suitable resolution, injective, for instance, suitable resolution of M Yeah, what resolution means that it is exact, so the kernel of the next arrow is coincides with the image of the previous arrow, and the kernel of the first arrow is M. So this is this is an exact sequence. Yes, if we add this. Yeah. So now we just apply a functor f to this resolution and calculate its cohomology. Okay. So well, there are something to check here, namely, first of all, that you know there are many choices for this resolution, so you have to check that the result does not depend on the resolution. Namely, if you have another, say j naught, another resolution like this, then there is a natural isomorphism between the cohomology of these complexes. So you have to check this. Well, and of course, when you try to check this, then instead of suitable, you put injective, and so to check that this is there is such an isomorphism for any injective resolution. Yeah, so we assume that there are enough injectives. And then another exercise to check that this you do have such a natural long exact sequence. Well, but this is more or less clear because it will become clear after you you construct. You see that if you have a morphism from M to M, you will have to construct. So you will have a resolution here, a resolution I, and you will have a resolution I prime, and then the exercise will be to construct a morphism between these resolutions so that they will induce morphism on the cohomology. Yeah? So if you have a morphism of complexes, then of course you get the induced morphisms of cohomologies, and then if you will have and then you will have to check that there are such. So if you will have to construct some kind of short exact sequences of complexes, and then of course if you have a short exact sequence of complexes, then you get a long exact sequence of the cohomology. Yeah? Okay, yeah, so that's about right exact functors of right derived functors of left exact functors, but also we will need, we will probably need, but I'm not sure. Yeah, sometimes it is useful to have also the notion of left-derived functors of right exact functors. Yeah. And yeah, maybe I have already mentioned one source of yeah, so maybe I should mention one important example of it is somehow it is presented already here, but let me mention it more explicitly. So assume we are dealing with arbitrary abelian category. So yeah, so example Example, the functor home from certain m. So, and the claim is that this functor is left exact. Yeah. So this left exact. You see that here is another functor but from opposite category. It is also left exact, but it is from the opposite category. Yeah, and yeah. So what about right exact functors? Of course you know some of them, namely from the category of A modules. You have the functor of tensor product here, tensor product M tensor A. This is the functor to abelian groups. Okay. Yeah, and so you might ask what is suitable objects for left exact functor. Well, of course you can simply pass to the opposite category, and then injectives in the opposite category will be suitable for. But injectives in the opposite category of A modules are called projective modules. Yeah, so suitable. So for all right exact functors, suitable are well, maybe I should put here. So projectives are suitable. Projectives. Yes. And there are enough projectives. So, and you see that a resolution in the opposite category will be in the opposite direction. So it will be M P naught P1 and so on. Yeah. Yeah, and so and of course in the category of A modules, of course there are enough projectives, because any yeah. So here what does it mean enough? Here enough was understood as any M is can be embedded into certain suitable object. Yeah, but here everything we reverse the arrows. So here enough means that any object is a quotient of yeah. So enough here this is different. Any object is a quotient of a suitable. Okay. Yeah. So. All right, but of course any A module is a quotient of direct sum of copies of A. Yeah, so of course we can always use projective resolutions if we are looking for left and right functors of right exact functors. Yeah. So yeah, that's it. Yeah, and let me just mention, yeah, there is a little trick when we will deal with these functors, home. But you see, here we see two kind of functors. The trick is that that we can yeah, derived functors. Well, let's call this derived functor of this functor. Let's call this Ri a m. This is called x I m. And the claim is that, yeah, you see that we can we have this functor and we have another functor. We have R I home a the functor on the opposite category n. Let's call it a. Well, so the claim is that omit this. The claim is that if we apply this functor to m, then the result will be the same as we apply this functor to n. Yes, so we can simply write here, yeah? Yeah, so you see that you may either use to calculate x, you can use injective resolution of n or projective resolution of m, whatever you prefer. Yeah, so depending on what is more convenient. Yeah, so yeah, maybe okay. So we're going to discuss this splitting. You see that we will deal with finite dimensional algebras over a field, and we will try to figure out whether it can be split into semi-simple part and its Jacobson radical. So, but before we need a lemma. So, yeah, it's a very simple lemma. We assume that A is again is a unital associative ring. Next, R is an element such that its product with the complementary to it is nilpotent. And the claim is that there is certain polynomial with integer coefficients vanishing at 0, such that its first of all, its value, the sum of its coefficients is 1, and its value at this element R is idempotent. Yeah, so theta. So we define theta as the value of this polynomial at R, and the claim is that it is a projector. Yeah. Yeah. So, well, this actually is some kind of version of, well, not a version, but some variation on Hensel's lemma. Yeah. So it's roughly speaking, we have to we have to solve you see that it is nilpotent, yeah, so we can try to just solve this this equation like so what happens if we solve the equation x squared is x, yeah? Do you know how to solve quadratic equations? Me too. Yeah, but this is a joke, yeah? So, it's 1, yeah, no? Yeah, 1 plus minus. Minus because we want this to start with, 1 plus 4x 1/2 over 2, yeah? And you see that x is big X is no. Maybe I should write small n. I don't know to mean that it is that it is nilpotent. Yeah. Yeah, and actually the point is that this is yeah. Maybe I should keep here x, big X, because I want this. To be, you see that you may ask what happens if 2 is not invertible, if there is no, yeah, so there are some questions. But the point is that what you get is a formal series with integer coefficients. Yeah, and so and now if you put here a nilpotent element, then this will be a finite sum. Yeah, so it's actually that's an idea. That's it's not a proof, but maybe you can prove this yourself. Yeah, so it's not a big deal. Okay, now we pass to. It's called Wedderburn-Maltsev splitting theorem. But before that, let me give one more definition. Yeah. So first of all, we have to define. How should, yeah, maybe before before defining Hochschild homology, we need, we don't need right now. Yeah, maybe we start with definition. So definition. So an associate. So we have a field K and an associative algebra. An associative algebra K. Sorry, A over a field K is called separable. Separable if A with extended coefficients with coefficients is semi-simple for any field extension L, any field extension L over K. Okay. There are several versions of these definitions. Yeah, but let's look more closely at this condition. So what does this mean? This means that well, for instance, if we take L equal to K, then this means that A itself is semi-simple. Yeah? And we know that semi-simple algebras are just finite direct sums of matrix algebras over division rings. Yeah. Okay, so this means that this is simply yeah, so this means that A is semi-simple, and now so we have matrix algebras over certain division rings, and we know that when we extend coefficients to L, then these coefficients of matrix algebras become what? Become the centers of these division rings, tensors with the L. Yeah, so this means that actually semi-simple whose center is a direct sum of separable extensions of K, separable extensions of K. Yeah, so because if you know, if what happens if you tensor, so you have, for instance, F, so if F is an extension of K, then what is the tensor product? It is, well, there are several options. If F over K is separable, then it will be just direct sum of several fields, yeah? And if if F is not separable, then as L you can take F itself, and you will get a certain nilpotence in this. So has a nilpotence if if F over K is inseparable. Yeah. So in particular, this definition coincides with the definition in the case of fields. Yeah. So you, as an algebra A, you can take a finite separable extension of K, and or it will be, sorry, it will be. Wait, it will be semi-simple. Yes, it will be semi-simple. Hold on. Yeah, it's okay. It's okay. No. Sorry. It will be yes. It's correct in the sense that it will be semi-simple itself. But if you extend coefficients, so for instance, if you take if F over K is infinite, then it's well, even a separable closure, yeah, even separable closure, yeah. Then the tensor product of F with itself will not be semi-simple. Is not semi-simple. Yeah. because semi-simple, you see that you have infinitely many, for instance, if you take a separable closure, yeah, so if you take separable closure, separable closure of F, for instance, then you take all possible. So on F, on this factor, you take the identity of some, at least some embedding, and on the second factor, you take all possible embeddings of F into into the separable closure over that are identical on K. Yeah. So you get many morphisms from this algebra to a field. Yeah. So this means that there will be infinitely many of them. So it is not a finite direct sum of. We know that semi-simple means that they have finite sums of matrix algebras. Yeah. In our case, everything is commutative, but so this matrix algebras are actually just fields. Yeah. So, but here we have infinitely many such summands. Oh, we don't have any summands at all, in fact, because yeah, but can really split them. Okay, yeah. So so, but in case of finite extension, it's a finite separable extension. It's okay. It's considered. Yeah, maybe in some proof. Yeah, we have to check that this is. Let's see. So what is evident? Well, evident that it should be. Of course, it should. What is evident and what is not? So of course, if all these algebras are semi-simple, then A itself is semi-simple. But if so, we want to know that that the center consists of a separable extension is a direct sum of separable extensions. Yeah. Yeah. So what happens if there is something? Yeah. So let's prove in this direction. Yeah. So if something contains if the center if the center contains center of A contains F which is not separable, yeah. F over K is not separable. Yeah. So so the claim is that it has nilpotence. Why? Well, actually, it's quite clear. You see that any extension, you can think of any extension as a two-step extension. Namely, the first one is how it's called separable. Yeah, separable. By the way, do you know what does it mean separable in the case of fields? Yeah, you can do this way, or you can say that this is just the set of those elements in F that are such that the Keller differentials vanish. Yeah, you can do this way. Yeah. Omega Keller differentials. Do you know what I'm calling? No? Okay. So да, ну в смысле, этот минимальный вещь, да? Ну да. Ну, можно так сказать, да. Но просто с многочленными, понимаете, значит, yeah, you see that you can say that the minimal polynomial of x is has no multiple roots has multiple roots and no field extensions. Yeah, you can. But the point is that it's not very convenient to deal with polynomials when you, for instance, you have to add two elements. How do you know what happens with that? Yeah, but with the differentials, it's much easier. So, so let me define this. It's in general. Well, in general, you can start with any associative ring, and now we consider. So this is fixed. This is fixed. Now m will be a variable. So this will be an a bimodule, and differentiation. What is so? What I'm going to say? What is a differentiation? Differentiation. Or derivation. I don't know. Derivation maybe. Derivation. Is a map, is a linear map, well, additive map from A to M, which is additive, well, additive, and maybe we should also fix a subring, or if we don't, we just take those subring generated by 1 and the minimal non-trivial subring. Yeah, so additive and satisfying the Leibniz rule. This means that the image of product is d of b plus d of a times b. Yeah. So these are derivations, and we can also, yeah. So the claim they form. So the derivations they form a category. Well, in the sense that if you have one derivation, you have another derivation in prime, then a morphism between them is just an arrow. So these are a linear, well, a bilinear, yeah, a bilinear. Well, a morphism of bimodals, yeah. A morphism of bimodals. Okay. Yeah, and if there is a final initial, so the initial object is denoted. The initial object is denoted in the following way. It is called. We can also consider not only. We can put an extra condition, namely we can ask that a d of a is 0 for all a in B. Yeah? And then the initial object in such a category is denoted in the following way. Yeah. And actually this object is defined very, very explicitly. Namely, you just well, let's assume that everything is commutative. So if A is commutative, like here, then then we don't care. Well, bimodules becomes just usual modules, and then omega you can say in the following way. So then consider the multiplication map from tensor square to A. So this is just multiplication map, yeah? This is surjective. And let I be its kernel. And then omega A and B is just I modulo I square. Yeah? And the map is given from A to omega is given by sending A to A by the class modulo I square 1 minus A. Okay? Or you can just you can think of this just as a formal. You see that what do you want? You want this this rule, and you can think of this just formally. So you can think of elements here just as a formal sums, like this, I from 1 to n. So this where AI AI and BII in big A, but you have to impose these conditions. Yeah, so you just say that D of A prime is well, you know what's this, and D of A is DA is 0 if A in B, and of course it should be additive, yeah, so it's dA plus dA prime, and yeah, so that's just impose these relations and write this way. Okay, but so but of course you can say that the problem is that when you think of multiple roots, it's not even evident that the sum of two elements are separable. Yeah. Well, here maybe it's not that evident, but at least well, maybe there is no big difference. Yeah. So. So
when you not only associative ring, but with unity, we need.
Yeah, that's right. But here you see, we assume that it is commutative, of course, with 1.
The last set is for general.
Well, you see that it's also for commutative because it is. Here we can multiply by elements of A on the right. Well, of course we can put it on the on the left, but of course we can put it on the right. But we will mean anyway multiplication on the left. Yeah. So when we deal with bimodules in the commutative case, we don't care whether we multiply on the right or on the left. Yeah. So here anyway so this. In a sense, what I'm going to define right now is depending on how much time I'll have. Maybe we have to stop here soon. But anyway, let's finish with this equivalence. So what is evident? So it's So the point was that if we have an arbitrary field extension, that it can be considered as a two-step extension. Yes, the first one is separable, and the second one is purely inseparable. Yeah, inseparable. So then you see we have Can you see here some importance? Yeah, maybe. Well, maybe it's easier. Yeah, maybe we can. Well, you see, we are free to choose this. Field. Just what do we want? We want that it is. Yeah. So F. Yeah, it's contained. Yeah, we can choose it. We can take its algebraic closure. Yeah, and then. Wait. Well, I had. Well, maybe we can just apply. We can just apply. So it has, maybe we don't even need this. We don't even need this, but simply, So we can, we know what are, so if it is a finite dimensional algebra over F bar, yeah? So this is a finite, well, an Artinian, yeah, Artinian and F bar algebra, yeah. We know what are semi-simple algebras, finite dimensional algebras. Well, maybe finite dimensional is better, yeah. Finite dimensional. Finite dimensional F bar algebra, yeah. If it was semi-simple, yeah, then it is a matrix. It should be a matrix algebra, yeah, or a division algebra over F bar. So what are finite dimensional algebras? Finite dimensional division algebras over F bar. Only F bar itself, yeah. Yeah, because you see that any matrix, well, any element. So we have a finite. We just what is a division algebra? It has certain element which is algebraic, or because it's finite, it generates a finite dimensional extension, yeah, and there are no finite dimensional extension of bar. Yeah? So any division finite dimensional division algebra of bar is F bar itself, yeah. So and it is commutative, so it is just it should be a finite sum of copies of F bar, yeah. So if it is semi-simple, then it is isomorphic to a direct sum of several copies of F bar. Yeah. But let's look at so what and then home. What is home from? Home as rings. Yeah. Home. Well, say it. f to the n. Yeah. So home as what? As k algebras. Home as k algebras. Not k algebras, as f bar algebras. Yeah. F bar. Yeah. So f bar what? F bar algebras. Yeah. F bar algebras. So this is here we have multiplication by f bar, and here, and yeah, so we can consider them as f algebras from f to f bar, f when to the n is should be wait, sorry, here I mean morphism to f bar. Yeah. So this is you see we have morphisms of f bar algebra from f bar to the n. So there are n elements. Yeah. So n element set. Yeah, so we can, the morphisms are just projections. So we have these summands, and there are no, yeah? Okay. N element set, yeah? So projection. Нет, именно просто n штук. You see that there are, you see what are the maximal ideals in this algebra? So there are, the maximal ideals are just sums of all but one summand, yeah? So there are n maximal ideals. All right, but now what are Home's here? So Home is f bar algebra from f tensor k f to f. This is the same as a Home of k algebra from f to f bar. And this is so this is another definition of separable extension. Yeah. So it should be, so maybe I should put here the cardinality, yeah? And cardinality is the separable degree, yeah? Separable degree, yeah? Degree of this extension f over k. Yeah. So if I want it to be n, then this extension should be separable. All right. Well, maybe we should stop because, yeah. Stop. Yeah. And I'll try to make some exercises. Ну, то есть, наверное, там что-то все это отчасти и так знаете. Можете отставить.
think exercises which professor.
Maybe the
We have a very good questions.
he have given two exercises in Google class. And order theory and this are almost
This is the 4 lectures.
yeah. For this part, we talk about some.
And you also work on the code formulas.
Which one?
And they just for this class.
7x
I'm sorry, I'm taking your time.
7x
7x.
EC 4 and then the last lecture we talked about some things theory the series.
I have this here forming this course.
This is the last lecture. We talked about this theory.
The basic motions and example of making which is curse number.
Maybe this is short and you can Google it. And this have talk about.
Okay, Jacobson Institute.
This is the last lecture. He want to give an example in which for ring is a theory, but not theory. This is the lecture is posted in Google Class, and this also, this is and this also. Maybe we did talk about this. Maybe stop here.
Okay. Then we have 3 exercises to do. Yeah, we was.
You can do the lecture he puts on the Google Class first. Yeah. Yeah, maybe this lecture in this class he will put in later.
Okay, in Google Class I will post to this.
Yeah, maybe
Okay,
when we finish the class, when we finish the homework about